In this video, we're going to be writing radicals of all different types into their simplest form. So in order to write our radicals into simplest form, we're going to start by using the properties of radicals, specifically that product property or that multiplication property of radicals, to rewrite them in a very specific way. So if you think back to earlier in your math career, you learned how to simplify square roots. So for example, say we had something like the square root of 98. And if we needed to simplify the square root, we would start looking at the perfect squares. So we wouldn't look at 1 because everything's divisible by 1, but we'd look at 4, 9, 16, 25, 36, 49, 64, 81, and then we wouldn't look at 100 because it's bigger than 98. But we would look at these perfect squares and we would use our calculator or our brains if you're good at division, and we would determine which of these perfect squares 98 is divisible by. And in this case, if I go through and I divide 98 by all of these perfect squares that are smaller than it, I would find that 98 can be rewritten as the square root of 49 times the square root of 2. And the reason I would do this is because 49 is a perfect square, so the square root of 49 would become 7, and I would get plus or minus 7 square roots of 2. So I could rewrite 49 as its perfect square, which was 7, and it would go into its simplest form. So we're going to do this same thing. We're just going to do it with all different types of roots, including the third root, the fourth root, the fifth root, and so on. So we're not just looking at square roots anymore. So here, if I look at this first example here, I notice that I have the third root of 135. So I'm going to go through this same process, but I know that I need to look at values or numbers to the power of 3 and figure out, is 135 divisible by any powers of 3? So I'm not going to look at 1 because everything is divisible by 1, but 2 to the power of 3 I know is 8. 3 to the power of 3 I know is 27. 4 to the power of 3 I know is 64. And 5 to the power of 3 I know is 125. And then 6 to the power of 3 I know is bigger than 135. So now if I start dividing 135 by these numbers, if I divide it by 8, I notice that the result is a decimal, so I'm not going to use that one. If I divide it by 27, I know that it turns into 27 times 5, so that's convenient. That one works. If I divide it by 64, again, I get a decimal, and 125, I also get a decimal. So what I'm going to do here is I'm going to rewrite this as the third root of 27 times the third root of 5. So notice that I'm just using that product property to rewrite 135 as a math problem, as a product. And when I write it as a product, I can split it up into 2 different radicals. So then from here, I know that the third root of 27 can be rewritten as 3, because 3 times 3 times 3 gives me 27. So notice that when I rewrite it as 3, the radical is gone. And then from here, I get the third root of 5. So in its most simplest form, this radical here that we started with would be 3 times the cube root of 5. Then if I look here at this next example, I see that I have the fifth root, so I'm going to look at numbers that go to the power of 5. And I'm looking for one that if I divide 128 by that number, it works really nicely. So here, if I think of my powers of 5, I know 2 to the power of 5 is 32. 3 to the power of 5 is 243. So that's already way too large. So I'm not going to look any further. I'm going to assume that it's either 132 or nothing. So if I divide negative 128 by 32, I end up finding that 32 times negative 4 gives me 128. Now, I like to actually remove the negative as I perform the root if I can. So I'm going to flip this around and do negative 32 times 4. So now what I can do, because I found a product, is I can rewrite this as the fifth root of negative 32 times the fifth root of 4 because negative 32 times 4 is negative 128. So I'm just using the product property here to split it up into a product of two things that multiply to be negative 128. Now from here, the fifth root of negative 32 is negative 2. This one stays, and I have my final simplified form. Now we're going to apply the same type of thinking to a situation that contains variables. And variables are actually pretty simple. You just have to pay very close attention to this radical out in front. So for this first one, I'm going to break this up into as many to the third powers as I can. So here I am going to leave 64 because I know that 64 is a cubed root. And then I'm going to take this 6 and I'm going to rewrite it as y to the power of 3 times y to the power of 3. Because remember, when we have common bases, we add exponents. So I can split it up, basically using that property backwards. And then I can write this as the cubed root of y to the power of 3. And then I have the cubed root of y to the power of 3. Now, the reason I'm doing this is because anything to the power of 3, I can take a cubed root of. So here, the third root of 64 is going to become 4. Then from here, cubed root of y to the third, well, those undo each other, so I'm just left with y. And same thing here. So my final answer here really becomes 4 times y squared. Now in the second example off to the right, I notice that 243 isn't a fourth root, so I'm going to focus on this number here first. And I'm going to look at the fourth roots that are smaller than 243. So I have 2 to the power of 4 is 16, 3 to the power of 4 is 81, and 4 to the power of 4 is 256. So that one's already too large. Now if I divide 243 by 16, that's a decimal, so that one doesn't work. But if I divide 243 by 81, I find that that's 81 times 3. So I'm going to break this up into the fourth root of 81 times the fourth root of 3. And then I'm going to start breaking these variables up into groups of 4 because it's the fourth root. So I can break x to the 10th up into x to the 4th, x to the 4th, and x squared because that'll total 4 plus 2 is 10. So I have fourth root of x to the 4th, fourth root of x to the 4th, and the fourth root of x squared. And then from here, the y can become y to the 4th and y to the 1st. So I'm going to have the fourth root of y to the 4th, and then I'm going to put this one up here, the fourth root of just y to the 1st. So now if I rewrite any of these that can be perfectly rooted, the fourth root of 81 is 3, so that one is rewritten. Fourth root of x to the 4th is x. This one becomes x as well. This one, because it's not an x to the 4th, can't be perfectly rooted, but this y to the 4th can be. So I notice that out in front I have 3x squared y, and then still inside of my fourth root I have a 3, an x squared, and a singular y. So on this slide, these already kind of look like they're written in some form of simplest form. But what we're going to focus on here is doing something called rationalizing our denominator. So when you're simplifying square roots, leaving a number in your denominator that has a square root is not good practice. That's considered an irrational denominator, and we do not want to leave those in our math problems. So we're going to rewrite this without square roots in our denominator. Now, we can do that in a really specific way. So here I notice that I have a fifth root in my denominator, and 8 is not a fifth root. So because 8 is not a fifth root, I have to think about how I can make 8 a fifth root. And so if I start thinking about the fifth roots that I know, so any number to the power of 5, I know that 2 to the power of 5 is 32. That is the fifth root. And I start thinking, okay, can I strategically turn 8 into that particular number? Well, I could if I multiplied it by the fifth root of 4. So what I'm going to do here is, in order to rationalize my denominator, I'm going to multiply both the denominator and the numerator by the fifth root of 4. Now notice that in doing so, I'm really just multiplying by 1 in a very weird way. Fifth root of 4 over fifth root of 4 is 1, because something divided by itself is 1. But in doing so, now I can use my product property, so my numerator in the top becomes the fifth root of 7 times 4, which is 28. And my denominator becomes the fifth root of 8 times 4, which is 32. So notice, by just strategically multiplying by 1, I now have something in my denominator that can be perfectly rooted. The fifth root of 32 is 2. So now I have a rationalized denominator that no longer contains a square root. Now if I look here at example 2, I notice I have my fourth root. So I'm going to think about what fourth roots I know. Well, 2 to the power of 4 is 16. 3 to the power of 4 is 81. 4 to the power of 4 is 256. 5 to the power of 4 is about 625. So I'm going to focus in on those and see if I can strategically multiply 128 by something to get one of these values. And when I start kind of experimenting, I realize that 128 times 2 gives me 256. So I can strategically rewrite this so that it has a denominator of the fourth root of 256. And I can do that by multiplying by the fourth root of 2 in both my numerator and my denominator. So here this becomes the fourth root of 6 times 2 is 12. And then it becomes the fourth root of 128 times 2 is 256. So now from here, I'm going to simplify the denominator because I can. So my numerator is going to stay the same because it doesn't simplify, but the fourth root of 256 is plus or minus 4. So here we're going to use our properties of radicals again, but we're going to use them on problems that contain variables, and we need to make sure that we rationalize all denominators. So here in this first one, I'm going to split this up using that quotient property. So this becomes the fourth root of x to the 12th over the fourth root of y to the 9th. So if I start splitting this up, at least in the numerator, I can see that I get the fourth root of, I can split this up into x to the 4th times x to the 4th times x to the 4th. So I can get that numerator part solved out pretty quickly. So that numerator I know is going to become x times x times x, which is just going to be x cubed. So I can see that piece happening in my numerator. Now what I notice about my denominator is that my denominator doesn't work out quite so nicely. This I can split up into y to the 4th times y to the 4th times y to the 1st. So that becomes the fourth root of y to the 4th, the fourth root of y to the 4th, and the fourth root of y to the 1st. So these two work out nicely and become y times y, but this last one doesn't quite. It's still y to the 1st. So we're going to have to do something here because we have y squared times the fourth root y to the 1st in our denominator. So we're going to have to do something different. So I'm going to rewrite this up here so I have a little more space. So this is x to the 3rd over y squared times the fourth root of y to the 1st. Now I know that if that y to the 1st inside the root was a y to the 4th, that this could be a perfect root and it would result in no longer having a root in our denominator. So what I'm going to do here is, in order to get that to be a y to the 4th, I'm going to multiply it by the fourth root of y cubed. Now remember, whatever I do to the denominator, I also need to do to the numerator. So now I'm just going to multiply across. So the numerator just becomes x cubed times the fourth root of y cubed, because they can't be combined. One's outside the root, one's inside the root. The denominator here becomes y squared times the fourth root of, well, y to the 1st and y to the 3rd become y to the 4th. So that then becomes x cubed times the fourth root of y cubed in my numerator, but then it becomes y squared times y in my denominator because this part right here can evaluate to just be y. So my final answer here is x cubed times the fourth root of y cubed all over y cubed. Now the last thing we're going to talk about here is what we do when we have a sum or difference involving a square root in a denominator. Now this focuses specifically on square roots, so this is something that is to the power of 1/2 or has a 2 for its root. So this is a very specific strategy. But what we can do is that if we have a sum or a difference involving a square root in our denominator, is we can multiply by something called the conjugate. Now the conjugate is a special relationship between two expressions where they contain the same first term, so here you see a times the square root of b, and the same second term, so here you see c times the square root of d, and the difference is that one has a plus sign in between and one has a minus sign in between. And you're going to see what happens on the next slide, that when we multiply by the conjugate, it will actually help us to strategically eliminate any square roots that might be in our denominator. So here if we take a look at example 1, you'll notice that we have a square root in our denominator, and it has a sum, which means that we're going to have to use that value called the conjugate in order to help us remove that square root. We can't simply just multiply by one single thing, like, the square root of 6 and get the square root of 36. It doesn't work because that plus 3 is also there. So remember, your conjugate is the same thing, but it has a different symbol in between. So this plus symbol is going to change to a minus symbol. So your conjugate is going to be 3 minus the square root of 6. So what we're going to do here is we're going to multiply by the conjugate. So we're going to multiply the denominator by 3 minus the square root of 6. And we're also going to multiply the numerator by 3 minus the square root of 6, because remember, we have to multiply this by 1. So we multiply the top and the bottom by the same thing. Now, I'm going to add some parentheses in down here. I might get a little bit confused. But what we're going to do is we're going to use big distribution, and we're going to multiply all of these items together. So if I start with the top here, I'm just going to utilize the distributive property. 5 times 3 would put 15 in my numerator, and then minus the 5 is on the outside, 5 square root of 6. So the 5 and the 6 can't be multiplied together, and that's simply because the 5 is not inside of a root and the 6 is. So they either both have to be inside or both have to be outside. Since they're one inside, one outside, they just stay one inside, one outside. Now, if we move on to this denominator, we're going to start with 3 times 3, which is 9. Then 3 times negative square root of 6, so that becomes a negative 3 square root of 6. Again, noticing 3 on the outside, 6 on the inside, because that's how they were to start. Then I take square root of 6 times 3, so that's plus 3 square roots of 6. And then I end up with minus, I have the square root of 6 times the square root of 6. Well, that becomes the square root of 36. They're both underneath the root, so they get multiplied together. So now if I start to simplify things, well, my numerator stays the same. It stays 15 minus 5 square roots of 6. That doesn't simplify anymore. But what I notice down in my denominator is I notice that I have negative 3 square roots of 6 and positive 3 square roots of 6. Well, those add together to be 0. So those are now essentially gone because they canceled out. Then I still have the 9 minus the square root of 36 is a perfect square. I know the square root of 36 is 6, so that becomes 9 minus 6. So notice I was able to simplify my denominator to be something different. And now if I continue simplifying this, this turns out to be 15 minus 5 square roots of 6 over 3. So notice that by multiplying by the conjugate, this special situation occurs where I get a plus or a minus, but they cancel out, and then I end up with this perfect square over here that evaluates. So my square roots are gone. So let's apply this same thinking one more time to this next example. So here again, I'm going to multiply by the conjugate because I notice I have a square root in my denominator, and I notice that there's a sum or a difference, which in this case it's a difference. So I'm going to multiply by, remember it's 8, then we change that negative to a plus, so it's the opposite sign, 2 square roots of 3. And then I'm going to multiply by that same expression in my numerator. So I'm going to start by adding in another set of parentheses here and then multiplying these out. So I'm going to start square root of 3 times 8. Well, my numerator becomes 8 out in front, square root of 3. Then I have plus, 2 out in front, and then the square root of 3 times the square root of 3, those are both underneath the root, so that becomes the square root of 9. All over, so I've multiplied those two out, 8 times 8 is 64. 8 times 2 square roots of 3, well, I can multiply the numbers together on the outside, so that becomes 8 times 2, which is plus 16 square roots of 3. And then I have a negative 2 square roots of 3 times 8. Well, negative 2 times 8 is negative 16 on the outside, square root of 3 on the inside. And then here, this next chunk, negative 2 times 2 becomes a negative 4. And then we have square root of 3 times the square root of 3, which is 9. So there I was able to simplify it just a little bit. Now I notice again that this special situation occurs where these cancel out, so those are effectively gone. Then I start looking for any perfect squares that I can simplify further. Well, what I notice is that up in my numerator, I have the square root of 9. So that can be rewritten as 3. So my numerator becomes 8 square roots of 3 plus 2 times 3. Then my denominator is 64 minus, well, this one also, square root of 9 becomes 3. So that becomes minus 4 times 3. So now if I simplify these just a little bit further, this numerator becomes 8 square roots of 3 plus 6 over 64 minus 12, which I can simplify further because the denominator can be subtracted a little bit further. So that becomes 8 square roots of 3 plus 6 over 52. Now, technically, this is the right answer, but if you look at all of the coefficients or constants, so anything not inside of a root, you will notice that 8, 6, and 52 are all divisible by 2. So we can simplify this by dividing each term not in a root by 2. So this becomes 4 square roots of 3 plus 3 all over 26.